Alright, in this video we got a special request, so we are going to be discussing arc length, radian measure, and the Pythagorean identity. If you want to pause the video real quick, I do have the individual formulas up here written above, so if you want to take a second to write those down, by all means, go for it. So first up, we're actually going to talk about radian measure, because radians will help us understand arc length just a little bit better. Let me see if I can focus the camera up a bit. So, radians are just another language of describing angles. I put an example here of bonjour and hola. Those are the exact same thing, just saying it in different languages. We're both saying hello. Degrees measure angles, radians measure angles. We just have a different way of doing so. The big conversion factor to bounce from one to the other is 180 degrees is the exact same value of pi radians. You could also make the claim that 360 degrees is the same as 2 pi radians. So when we go from one format to the other, we're going to either bounce between, use the conversion factor pi over 180 or 180 over pi, and that's depending if we're going degrees to radians or radians to degrees. So here I've got a bunch of examples, and we're going to zip through degrees to radians or radians to degrees, and I feel like once we see a few examples, the pattern should become pretty clear. So if I'm going from degrees to radians, I need to multiply by my conversion factor of pi over 180. Keep in mind, pi over 180 is technically the same thing as saying 1 because pi radians and 180 degrees have the equivalent value. Right now, I'm just going to carry the pi along. And ultimately, I'm just really reducing the fraction 120 over 180. Well, I can think of that as reducing the fraction 12 over 18. They both can reduce down by a factor of 6. So 12 divided by 6 is 2, 18 divided by 6 is 3. So 2 pi over 3 would be the radian measure. Next up, we have 2 pi over 3 radians. Well, I know that's going to end up turning into 120 degrees because we just did that. But for the sake of argument, let's see why that is. My conversion factor from going radians to degrees is going to be 180 over pi. Again, this fraction is still technically 1, but right now I need to divide the pi away so that I'm left with just whole numbers. So the pi's would cancel, and I'm left with 2 times 180 over 3. So you could either think of this as 2 times 180, figure out that is 360, and then divide that by 3. What I personally like to do is I like to take 180, and I'll divide that by 3, and I know that that's 60, and then I'll just multiply that by 2. We're doing the exact same operations here, it's just whatever order you want to think through it in your head. I personally like to shrink my numbers down as quickly as I possibly can. All right, 300 degrees. To go from degrees to radians, we're going to throw pi up top, 180 down below. Essentially, I'm simplifying the fraction 30 over 18. Again, both reduce down by a factor of 6, and that would be 5 over 3, and we just have the pi joining along for the ride. 7 pi over 6. We're going to multiply here by 180 over pi because we're going 2 degrees. So the pi's cancel, and I'm left with 7/6 times 180, or 7 times 180 over 6. Well, I'm going to think of this as 180 over 6, that's 30, and then times 7 would be 210 degrees. Next up, we're going to get slightly uglier problems. Let me zoom down here. From 100 degrees, I'm going to go pi over 180. Essentially, that's a multiplication, not an open circle. I'm simplifying 100 over 80, which is the same as simplifying 10 over 18, my bad. I can divide out a 2 from both, so that would be 5/9. And we throw a pi on there. And lo and behold, we get the same thing down here. So let's see what it looks like going the opposite direction. Pi's would cancel. 180 over 9 is 20 times 5. Well, that's 100. Surprise, surprise. So that's how we bounce back and forth from degrees to radians. It's really just fraction operations and getting a comfort level with that. Next up, we're going to jump into arc length. So S equals r theta, where S represents the arc length, r is going to be the radius, and theta is always going to represent an angle. but it has to be in radians. So more times than not, well, in this class it's going to be always, you're going to see pi in your theta. So I've got two examples here. We want to find the arc length given the information here. Again, the formula is S equals R theta. For all of these problems, you'll be given two of the three letters. You have to work backwards to find the third. Right now I'm given R and I'm given theta. Cool. The only problem here is theta is in degrees. And we don't like degrees for this formula. We want radians. So 30 degrees converted to radians, let's see. 30 over 180 is going to be 1 over 6. So that's really 1 pi over 6, or pi sixths. So I'll have S equals my radius, which was 6, times my theta, which was pi over 6. If I multiply this together, 6 pi over 6, the 6's cancel. My arc length would be pi centimeters. Make sure we're including our labels there. Next problem, again, we're given two pieces of information. I'm given the S value is 6 pi. I'm given the R is 4, and I have no idea what the theta is. So I'll divide 4 to the other side. Theta equals 6 pi over 4. Simplify if we can, 3 pi over 2. And no naked numbers, we're dealing in centimeters. So we label up our answer. Done and done. Final request problem type was a good old Pythagorean theorem, which is listed here in case you didn't get it before. Sine squared theta plus cosine squared theta equals 1. This is a great method if you're comfortable with basic fraction operations. However, if you're a little shaky with your fractions, I would strongly advise just drawing a picture. You're still going to be using the formula, but it's going to be disguised within the picture, and you won't really realize that you're doing it along the way. So first off, sine of theta is 2/3. That means sine squared of theta would equal 4/9. So that's one thing to keep in mind. I'm just squaring top, squaring the bottom. If I'm in quadrant 2, I know that cosine of theta is going to be negative in quadrant 2. So let's go through and solve this. I've got sine squared theta plus cosine squared theta equals 1. We already discovered that sine squared theta was really just 4/9. So 4/9 plus cosine squared theta equals 1. We will subtract this to the other side. So we're subtracting the 4/9. Cosine squared theta equals 5/9. Square root to find cosine. I don't know the square root of 5, so I'll just leave it as rad 5. Square root of 9 is 3. So the cosine of theta is going to be rad 5 over 3. However, it's in quadrant 2, so I need to make sure I throw a negative out front. So that's how we do it using the formula. Here's how I would strongly advise you do this without it. First, when in doubt, draw it out. So draw a coordinate. I know we're in quadrant 2, which is up here. So I'm going to draw my picture starting from the origin. I'm going to go out into quadrant 2, however far I deem necessary. And then I'll drop down straight to the x-axis and I'll make a right angle. They told me that the sine of theta, well, sine is the opposite over the hypotenuse. The sine was 2 over 3. So my theta is always going to be in by the origin. The opposite side was 2. The hypotenuse is 3. Well, I can do some quick Pythagorean theorem here. A squared plus b squared equals c squared. I'll save you the torment here. That's going to give me a rad 5 right there. And since we're on the negative side of the x-axis, I'm going to call that a negative rad 5. I realize having negative lengths doesn't particularly make sense, but it's a good reminder for this type of problem. Now, the reason I like doing this way, even though it does take more time, is I can easily get the cosine adjacent over the hypotenuse, negative rad 5 over 3, which we already knew. Or if I really wanted, I could also get the tangent, 2 over negative rad 5, and I can make that pretty from there too. So hopefully that helps clarify things. If you have further questions, do not hesitate. Just send me an email, let me know.